Hello, everyone, and welcome back. We're at the very last part of Chapter 6 on improper integrals. Now, what is this? So before I get into that, it's been a while since we've done too many integrals, so let me do a quick example of one. So let's do an example of 1 to 3 of x squared dx. So again, visually what that's saying is you're looking at a function. In this case, I put x squared, and you're looking at the area under the curve. Yeah. So visually, again, that's what you're doing. And the way we evaluate integrals is you have to use the antiderivative. So the antiderivative of x squared is going to be x to the third over 3. And then we're going to evaluate that from 1 to 3. And again, the antiderivative is the function such that when you take the derivative of it, you return to where you're at. And I could see that if I took the derivative here, that 3 in front, well, those would go away, minus 1, you get x squared. And then plugging it in, you would have 3 to the third minus 1 to the third over 3. And your final answer here would be 26 thirds. And that's the area under the curve. Okay. Now, let's look at another example. What if I gave you the integral from 1 to 2 of 1 over x squared dx? Now, visually, what does this look like? Is 1 over x squared is there's an asymptote at 0, and it would look something like this, where it's approaching the asymptotes as it gets closer to 0. Now, but what I want to do is just go from 1 to 2, in this range here, find that area. Okay. So the antiderivative there, so remember that that's the same as x to the negative 2. So my antiderivative there is if I add 1, I'll get negative 1, and divide by that entire amount down here. So I'm going to get negative 1 over x is the antiderivative, because again, that's going to give you x to the negative 1 over negative 1. And I just rewrote that there. From 1 to 2. And if you evaluate that, you'll be at negative 1/2 minus negative 1 over 1, which gives you negative 1/2 plus 1, which is 1/2. And that's great. And you could remember do this on a calculator, and that's great, where you have math, function integral, and you said, okay, what's the integral from 1 to 2 of 1 over x squared dx? And notice how I get 0.5, and that's just like what we believed. All right. Now, you can't use calculators, though, because if you're doing the AP exam, this is very much a non-calculator question, where they would ask you to do this without a calculator. Now, let's get into what improper integrals are. Oh, let me just do it over here. Side note, if I did the integral of 1 over x dx, what's the antiderivative of 1 over x dx? If you try to do our trick with the power rule and write that as x to the negative 1, and then you add 1, well, you'll get x to the 0, and then divide by that, you'll get 0. Well, what's that? Notice that it doesn't work. Remember that the antiderivative of 1 over x is going to be the natural log of x, plus c. Because recall that the derivative of natural log of x is equal to 1 over natural log of the base, which is e, times x, which ends up becoming 1 over x. So a little side note that I think working with a few students that has gone unnoticed with what we determine when differentiating log functions, that now we can do the integral of 1 over x. All right, so take a look. We're going to do this same problem of the function 1 over x squared dx, but instead of going from 1 to 2, let's go from 0 to 1. Or not even 1, 0 to 2. So now what we're doing, if you look at this visual picture, is you have your asymptote at 0. The function looks something like that as it approaches 0, the asymptote, and then approaches 0 over here. And then from 0 to 2, but notice that the area under the curve is getting infinitely large because, again, it's an asymptote. So that is what we call an improper integral, where one definition of it is that the area under the curve in a closed space, because again, we're saying from 0 to 2 in a closed space is infinite, infinitely large. All right? So how do we go about this? Is we actually have to solve this using limits. So instead of saying 0, because 0 is going to be hard to work with here since it's getting infinitely large, we're going to say some value, and I'll call it a b here. Why not? And then we're going to throw the limit as x approaches b from the right, or not from b. What am I saying? Limit as b, because I chose the very valuable b, approaches 0 from the right. And then the function is still 1 over x squared dx. And then we evaluate this. So what's this going to become? You're going to have the limit as b approaches 0 from the right, and the antiderivative of 1 over x squared is negative 1 over x. And we're doing this from b to 2. Okay. And then what you'd have here is that the limit as b approaches 0 from the right is going to be negative 1/2 plus 1 over b. But what happens here is if you plug in 0, you're going to get negative 1/2 plus 1 over 0 if you evaluate that limit now. Well, that is undefined. So what does that mean? That means that this does not equal a number. And what we call when that equals that is that means that it diverges. The area under the curve does not converge to a number. And you can see that in our work here, we got undefined. And to show you that on a calculator, take a look at this. If I try doing that same problem, but instead of 1 to 2, notice if I put in a 0, I hit enter, that tick mark means it's thinking. It's trying to calculate the area under the curve, but this area is getting infinitely large. It keeps going, it keeps going. Calculator's saying, hey, I'm still trying, I'm crunching numbers, Mr. Hine. Wait a second. And while I'm waiting more than a second, calculator, you're a little slow. There you go. And it says not met, because again, it diverges. It doesn't approach a number. A calculator couldn't figure it out. So that's the idea there. All right. Now that's just one example. Don't be thinking, although you might be thinking, does everything diverge? That's not true. It's actually quite interesting. Others converge. So let's look at another example. So let's do a new piece of paper. Have it back. Yeah. So what if we look at that same problem, but now we go from 2 to infinity of 1 over x squared dx. So visually again, you have an asymptote at 0. The function is approaching the asymptote, and it's approaching 0. But now we're going from 2 to infinity. So we're looking at this area under the curve here. All right. Now that's also infinitely large. Now notice that when I write it like this is also considered an improper integral. So there's 2 of them here. So I said previously it's when the area under the curve in a finite space or closed space is infinitely large. And then the other one, which you see here, is if one of your bounds of your integral is infinity, plus or minus infinity, which is here. So same way as before, how do you solve this? You have to solve using limits. Have to use limits, okay? And it makes more sense here in the sense that 2 to infinity, where infinity is not a number, infinity is a concept. So we can't plug infinity on a calculator, so we have to use limits to account for that, which is how we've done it all year with, especially when we did integrals, talking about how all those infinitely many small rectangles add up to make the area under the curve. But we had to use a limit for that Riemann sum. Anyway, here we go. So it's going to be 2 to some letter, and I'll call this in this problem k, of 1 over x squared dx. But then what's k is going to represent the limit as k approaches infinity. And now we can solve this. So the limit as k approaches infinity, the antiderivative there again is negative 1 over x. And we're going from 2 to k. So what you end up getting here, if we evaluate the limit, well, let's not evaluate it yet, go one more step, is we'd have negative 1 over k minus a negative, so that's going to be plus 1/2, in which this is now going to give negative 1 over infinity plus 1 over half. But what's great about this is 1 over infinity, as that gets large, that's going to approach, this whole thing approaches 0. So what we get is 0 plus 1/2, which is actually a half. Which means that this doesn't diverge, it converges to a half. So that area under the curve, even though it's infinitely large in a way, it's going to converge to the number 1/2, which is very different than what we looked at just previously on the back, is when we did 0 to 2, we got that it diverges. All right, so there's the idea of both. So that's improper integrals, and let me just do maybe 2 more examples with you so you get a better idea of it, and then I'll be done. So the first one, example, let's do one more, and I have it here, negative infinity to 2 of 1 over x minus 3 dx. Okay. Now, what's the antiderivative of this? Now, you can't use the power rule because, again, this is to the power of 1. So what that means is that the antiderivative of this is going to be the natural log. Well, I made a big mistake, and if this were the AP exam, they would have been so mad at me, I would have lost the point. I can't start doing this because of an infinity in the bound. It's improper. So I have to rewrite this first. Let's use B. Well, let's use A. Why not? A to 2 and do the limit as A approaches negative infinity of 1 over x minus 3 dx. Now, because we can evaluate this, so then that will be the limit as A approaches negative infinity of the antiderivative of that, which is going to be the natural log of x minus 3 from A to 2. Okay. Because again, if you take the derivative of this, the derivative is 1 over your input, which is 1 over x minus 3 times the derivative of the inside, which is 1, doesn't affect it here. All right. Evaluating this, we'll have the limit as A approaches negative infinity of natural log of 2 minus 3 minus the natural log of A minus 3. And if I were to evaluate the limit now, you would have natural log of negative 1 minus natural log of negative infinity minus 3. Now, what's natural log of negative 1? Well, that's asking you e to what power equals negative 1. Now, remember, e is a number. E is 2.71828 approximately, Euler's number. And you can't raise it to a power to get a negative number. So this is no solution, no real solution. So what that implies is that this diverges. This is not going to go converge to a finite area. Okay. And then the very last example, let's do the integral, which one now, of negative 3 to 5. Do I want to do this one? Yeah, this one's fine. Let's do the integral of negative 3 to 5 of 1 over 2x plus 6 dx. Okay. I can rewrite this as negative 3 to 5 of 1 over 2x plus 3 dx, in which that factor of 1/2 I can pull out in front just to not deal with that and rewrite it in a format that maybe we recognize, x plus 3 dx, in which the antiderivative of this is going to be 1/2 natural log of x plus 3 from negative 3 to 5. Now, just like before, I'm going so quick, I'm messing up. This all would have lost a point on the AP exam, because if I tried plugging a negative 3 either way, I can't actually evaluate this integral. So I'm actually writing something that is mathematically incorrect, because I think if we look at a graph of this, at negative 3, you have a vertical asymptote. Let's look, let's see, make sure we get this right. So if I did 1 over 2x plus 6 and graph it, yeah, so you have a asymptote at negative 3, and it looks something like that. So if we're going from negative 3 to 5, which is way over here, this is an improper integral because the area under the curve is getting infinitely large. So all of this is technically, I don't want you doing that because it's bad math practice. So at that first step, we should have rewrote this as some value, and for my mistake, I'll use m to 5 of 1 over 2x plus 6 dx. And then we're going to do the limit as m approaches -3 from the right, because that's where we're talking about the area under the curve, in which this is the more proper way of writing this. You approach -3 from the right, the antiderivative of that, which we talked already about, is going to be 1/2 natural log of x plus 3. That's the way we did as the 1/2 is in front there, and we're doing this from m to 5. So then what we'll get here is the limit as m approaches -3, and it'd be 1/2, and then it's going to be natural log of 5 plus 3 minus the natural log of m plus 3. And if I now evaluate my limit, we'll be at 1/2 natural log of 8 minus natural log of 0. Now, natural log of 8 is a number, that's fine, but what's natural log of 0? E to what power gives me 0? That does not exist. You can't raise it to a power and get 0. The only way you multiply to get 0 is if you multiply by 0, which is not happening here. So all of this implies that this diverges. So that's what an improper integral is. Again, we're talking about the two ideas of it's either when the area under the curve in a closed space is infinitely large, and this is where you have to be careful of this was a free response question. Make sure you rewrite it with limits. Don't make my mistake that I did here, because that's just a silly mistake that they would dock you on of mathematically accuracy when writing. Or an improper integral is when one of your bounds is infinity, like this one here, in which idea you have to use limits to solve, and your answer will either converge or diverge. Okay? And that's what this lesson's on. Hope that helps. If you have questions, don't hesitate to come to office hours or send me an email or something. All right, bye-bye.